right, we're going to continue on looking at a percent ionization comparison. This follows your polyprotic acid calculations that we were just working on. It should be a little bit quicker than what we just went through. So where this topic comes from is questions we've seen where it's asked students to kind of understand and make a comparison of how the percent ionization is affected for a weak acid at different concentrations, or sometimes you being able to pick out that if you dilute a weak acid, how is the percent ionization affected? So we're actually going to run through two of the calculations here, so that way you can see the comparison before I just tell you what it is. So this is going to follow on with what we've been doing so far. So hydrogen cyanide, which is a weak acid, is going to react with water. So you're going to see the same type of setup, and this is just good practice for weak acid calculations. So we have our hydrogen cyanide. It's going to react with water. Hopefully at this point you're getting pretty comfortable with these calculations. And then we have, with the formation of hydronium, we have the cyanide ion that remains. So we're going to set up our ice table. Since this is a weak acid. All right, our initial concentration that we're given is 0.75. And then, as usual, we're going to be filling in zeros to start with for our products here. And again, remember that hydronium, while there is a tiny amount of it present from the ionization of water, we can ignore it, or it's insignificant at this point. So then using our balance equation and the fact that this is going to proceed right towards equilibrium, we can then finish the rest of our ice table. All right, going ahead then, we're going to use, and I'm going to kind of simplify this here because of space, use our Ka, which is equal to 6.2 times 10 to the negative 10, which would then be equal to x squared. And then we're going to just go right ahead and simplify this to 0.75. And what we find is x, which remember is our concentration of hydronium here, is equal to 2.2 times 10 to the negative 5. So if we then go ahead and figure out our percent ionization, okay, remember this is the amount of hydronium that was formed from the ionization, or how much of the HCN actually ionized over the original concentration. So we're going to have 2.2 times 10 to the negative 5 over our initial concentration of the weak acid times 100. So the percent ionization ends up equaling 0.0029%. All right, so that's at the 0.75 molar hydrogen cyanide. If we then go through the same thing with our 0.25, so I'm just going to quickly copy in our equation here. And then just setting up our ice table, except in this case, we're going to use 0.25. For the initial concentration. Having these similar changes in x here. And then I can go ahead, in this case, the same Ka. And then just going ahead with x squared over that 0.25. We're just going to make that assumption right off the bat. X, which is the concentration of hydronium, is going to equal 1.2 times 10 to the negative 5th. Now, one initial thing to point out is, as expected, there is less hydronium that's formed from the initial concentration of 0.25. That makes sense. There's less hydrogen cyanide to start with in solution, and based on the fact that they have the same Ka, because it's the same weak acid, there's less or a smaller amount of hydronium. However, when we figure out the percent ionization, so we're using that amount of hydronium that was produced, okay, which is related to how much of the hydrogen cyanide ionized over the initial 0.25 concentration, the percent that ionized ends up actually being 0.0048%. So if we compare those two, in terms of the amount of hydronium divided by the initial concentration times 100, even though there's less hydronium at the lower concentration, you actually end up calculating a higher percent ionization. So if we originally just had a 0.75 hydrogen cyanide as our weak acid, one way to increase the percent ionization would be to actually dilute it to a lower concentration, which would then cause the percent ionization to increase. So we always like to go through these calculations because it's just something that has popped up that students, you can't really think through if you only have a minute and a half to answer it. So which acid solution actually had the greatest ionization? What's the relationship between molarity and percent ionization? You kind of summarize that for yourself. It's just that idea with, you know, the solution of a weak acid with the lower concentration or molarity has the greater or higher percent ionization. Okay, and that's it for this part.